Hey everybody, it's Jenny Civy and welcome to NSW PEP Talks, our new video series about data centers for our NSW PEP division. Last week I talked about some cooling basics and I wanted to move into power basics this week, but before I get into power for data centers, I want to talk about power in general so that I can make sure I cover some terminology and some basics. So let's get started. Let's start with a basic circuit. It can be drawn like this. You'll need a source for power. It could be a battery or the power in the wall. And you'll want a load because if you don't have a load, what would you be powering? So this could be a light bulb or a motor or a server rack. Electricity needs a closed loop to flow. Electricity flows from negative to positive, so the electrons in this loop are flowing in this direction. The flow of electrons is called the current and it's measured in amps. Voltage is the potential difference between 2 points. It's the force that is applied to the electrons that causes the current to flow. If this was an HVAC system, this would be the pressure that pushes the air through the ductwork. Voltage is measured in volts, and it'd be measured across here. We'll probably be showing some basic wiring diagrams in the future, so let's look at some basic components. We already saw the battery, which looked like this. We also have alternating power sources, which would look like this. You usually have a switch of some type to open the circuit and stop the flow of electricity, and that would look like this. Next, we have capacitors, which would look like this in the diagram. They temporarily store electrical energy. Next are inductors, which resist changes in electric current. When current flows, energy is stored in a magnetic field, and they would look like this on diagrams. And then we have resistors. They reduce the current flow and lower the voltage, and they'll look like this. Let's move all this over. You will also see series and parallel circuits. If something is wired in series, one thing is wired after the other, and it would look like this. So when it's on, all 3 light bulbs will be on. But if one light bulb is missing, it creates an open circuit, and the current will stop flowing, and then all the lights will be off. Christmas lights are usually wired in series. This is why if one bulb goes out, the whole string won't work, and you have to go bulb by bulb till you find the bad one, because the burnt out bulbs act like a switch that's open in the circuit. You can also wire things in parallel, which looks like this. In this case, when it's on, all the bulbs are on, but if one of the bulbs goes out, the other ones will stay on because there's a complete closed loop for current to flow through these other 2 bulbs. Let's move this over again and look at direct current and alternating current. In direct current, DC, the electrons only move in one direction. If you looked at voltage over time, it would look like this. The voltage would be pretty much the same all the time. Typical voltages are 12 volts, 24 volts, 48 volts, 380 volts, and 575 volts. In alternating current, AC, the voltage source switches back and forth. AC current would look like this over time. Typical voltages are 120 volts, 208 volts, 240 volts, 277, 480, 4160, and 13.8 kilovolts. Low voltage goes up to 600 volts, medium goes from 2400 to 69,000 volts, high voltage is from 115,000 volts to 230,000 volts, extra high voltage is 345,000 to 765,000 volts, and ultra high voltage is 1.1 million volts. Slide this over again and look at 1-phase and 3-phase. In single-phase power, a single branch provides power. Electricity flows through one alternating current waveform. The drawing that I showed earlier for AC is basically single phase. Single-phase power has 2 wires, one for power, the live wire, and a neutral. Single-phase power is commonly used in residential settings, small businesses, or lower power demand applications like lighting, heating, and household appliances. Think of things like refrigerators, TVs, and microwaves. 3-phase power has 3 alternating currents that are out of sync with each other, providing continuous power. This is what it would look like, where one of these is line 1, one of these is line 2, and one of these is line 3. It's typically used in industrial setting, large businesses, or for equipment that requires more power like HVAC systems, heavy machinery, and data centers. Three-phase power is used for its efficiency and ability to handle higher loads. It uses 4 wires, 3 live wires, and a neutral. Let's slide this over a little bit. You can use three-phase power to power a lot of different needs. You can pull all 3 phases to power a 3-phase motor, and you'll often see 3-phase written like this. Or you can just pull a single phase to power plugs or lights. You can also get different voltages based on how it's wired, either in a delta or Y configuration. And I have a video in HVAC Academy that explains this that I'll link below. There's also frequencies. So you'll see 50 Hertz in Europe and Asia and 60 Hertz in the US. 50 or 60 Hertz refers to the number of times the electric current changes direction per second. It's the frequency of the waveform. 60 Hertz systems alternate current 60 times a second, and 50 Hertz alternate 50 times a second. Let's move up to the top and talk about watts, kilowatts, and kilowatt hours. So first of all, what is a watt? A watt is a unit of power that measures how quickly electricity is being used at a given moment, and it's shown as W. Watts is equal to amps times volts. A kilowatt is 1,000 watts, and a megawatt is 1,000,000 watts. Now let's look at kilowatts and kilowatt hours. A kilowatt is the power that is needed for the appliance to work. A 1 kilowatt device is using 1,000 watts of power at any given second. A good analogy is to think of water flowing through a hose. The kilowatt would be the flow rate of the water. A kilowatt hour is the energy used each hour the appliance is running. It's how much energy has been used over time. So in our water example, a kilowatt hour would be how much water is in the bucket after it runs for an hour. So if we have a 5 kilowatt piece of equipment and it runs for 5 hours, you have 25 kilowatt hours of energy usage. So let's bring all this back on screen. I think that covers the fundamentals of power. We should have enough basics now to start talking about data center power next. Don't forget to like and subscribe to our YouTube channel, and thanks for watching.